Hello class, I'm going to discuss experiment 20, the first experiment we're going to do in chemistry 1103. In this experiment, we're going to determine the rate law for a chemical reaction, the iodination of acetone, which is an acid-catalyzed reaction. So the reaction will follow this stoichiometry. It involves acetone reacting with iodine to make iodinated acetone and hydroiodic acid. The reaction is acid catalyzed, and so we'll have to include not only the two reactants, but also H plus in the rate law. We can define the reaction rate for this reaction thusly, that the rate is always equal to the change in concentration of one of the reactants or products divided by the amount of time necessary to affect that particular change in concentration. If we're talking about reactants, we'll need a minus sign in front. So for acetone and iodine, we have minus the change in concentration divided by the time necessary. But for the products which are appearing in time, so their concentration is going up as time is going up, making a positive ratio, we don't need the minus sign. The minus sign is necessary for the disappearance of the reactants because the rate of a reaction is always positive. A negative reaction rate would imply that the reaction was running backwards. So what we'll focus on for this particular reaction is the definition of the reaction rate in terms of the time rate change of the concentration of iodine. Since iodine in solution makes a colored solution, by looking for the color to disappear, we know when the concentration of iodine has gone to zero. So the difference in concentration is just the difference between the initial concentration and zero. Technically, it would be zero minus the initial concentration, which is a negative number, which is why we need the minus sign. The rate law, then, we can determine by measuring the rate of the reaction and assuming a form and seeing if, in fact, the data supports the form that we have assumed. So the form that we'll assume is that the rate of reaction is proportional to the concentration of acetone raised to the mth power times the concentration of iodine raised to the nth power times the concentration of H plus raised to the pth power, where M, N, and P are the order of the reaction with respect to acetone, iodine, and H plus respectively. We'll determine values for M, N, and P using the method of initial rates. Once we've determined M, N, and P, and we have a whole set of rates, we can also find a value for the rate constant. So using the method of initial rates, what we need to do is we're going to measure the rate of reaction by changing the initial concentration of one reactant at a time. So we'll need a total of 4 runs in this case, 1 reference run, and then 3 where we change the concentration of each reactant of interest once. So let's consider, though, just 2 such runs. So for our first run, we're going to make the solution our initial and determine our initial concentrations from the following recipe, where we take 10 milliliters of 4 mol per liter acetone plus 10 milliliters of 1 mol per liter hydrochloric acid plus 10 milliliters of 0.05 molar iodine, and then 20 milliliters of water to make the total volume 50 milliliters. We'll measure the rate of that reaction and then compare it to the rate of the reaction for a mixture that's created by taking 20 milliliters this time. Notice that the volume has increased by a factor of 2, so that the initial concentration of acetone will have doubled in this second run relative to the first. We'll use the same volumes of hydrochloric acid and of iodine, and now, since we've added 10 milliliters of acetone solution, we require only 10 milliliters of water to bring the total volume up to the same 50 milliliters. Since we've doubled the number of moles of acetone by doubling the volume that we use of the stock solution, and the total volume for the solution is the same, the concentration, the initial concentration of acetone is doubled in the second run relative to what it was in the first run. Now, using the method of initial rates, what we'll do is we'll take the ratio of the 2 rates. So remember that the rate under conditions 1 was determined by this rate constant times the concentration of acetone under conditions 1 to the mth power times iodine to the nth power and H plus to the pth power. We measure it again under conditions 2. We get a different rate. The only thing that has changed now, though, going from run number 1 to number 2 is the concentration of acetone. Iodine and hydrogen and the rate constant all remain the same. So if we take the ratio of these two things, any dependence on iodine concentration, hydrogen ion concentration, or the rate constant is all going to vanish because they'll simply divide out. So if I take the rate number 1 divided by rate number 2, I'll get this ratio. And since we very carefully doubled the concentration of acetone in the second run relative to that in the first, that ratio is just 1/2 to the mth power. Now the ASA does need a correction on page 158, question 3 at the top of the page. Should change the recipe. So instead of using 20 milliliters of HCl, use 20 milliliters of acetone, and that should fix things so that you can address the rest of the worksheet. But let's go through some sample calculations to show how the calculations are done that you'll need to do to get through the ASA and also through the laboratory. First, let's show the calculation of an initial concentration. So let's suppose that we prepare a sample using this recipe. So we take 10 milliliters of 4 molar acetone solution, 10 milliliters of 1 mole per liter hydrochloric acid, 10 milliliters of 0.05 molar iodine solution, and 20 milliliters of water to make the total volume 50 milliliters. To get the concentration of iodine, I need to take the initial volume times the stock solution concentration divided by the total volume of the diluted solution, so the total of all of these volumes was 50 milliliters, and I get 0.01 mole per liter. Likewise, I could calculate the initial concentration of acetone by taking its volume times the concentration of the stock solution divided by the total volume of the solution. I get 0.8 moles per liter if I use 10 milliliters. Obviously, I would get twice that if I use 20 milliliters. Okay, so once we've gotten the concentrations, now we can focus on calculating an actual chemical reaction rate. So remember that the reaction rate was determined by taking the change in the iodine concentration divided by the amount of time necessary to affect that change. And since iodine is a reactant, it's going away. That change in concentration is negative. The final concentration is lower than the initial concentration. I need a minus sign in order to make the rate positive. So the final concentration is going to be 0 since the iodine is completely consumed. And the time needed for this to happen, let's say, is 230 seconds. Then the rate of the reaction is going to be given by the final concentration of iodine minus the initial concentration divided by the time necessary to affect that concentration change. I need the minus sign because you notice that the numerator here is a negative number. And so that the rate will come out as a positive value. The units on the rate are moles per liter per second, which is what you would expect since we have concentration divided by time. Now the next calculation we'll look at is the calculation of a reaction order by taking the ratio of two measured rates. Since concentrations of iodine and H+ don't change, and the concentration of acetone was doubled, we don't need to worry right now about the order with respect to iodine or hydrogen. We're going to worry only about the order with respect to acetone. But setting up the calculation or setting up the problem the way that we did, since iodine and H+ dependence are going to be removed, and we carefully doubled the concentration of acetone, this term is going to turn into just 1/2 to the mth power. These two values we've measured experimentally. And so here are the two experimental values that were measured. It's equal to 1/2 to the mth power. To solve for m, what I can do is take the natural log of both sides, and that will bring the m down from being an exponent to being a coefficient. And now by dividing both sides by the natural log of 1/2, I can solve for m, and I get a value of m equals 0.94. Now typically orders of these chemical reactions, not always, but typically they will be integers, or they could be half integers. It's fairly safe to say that this is actually representing an m equal to 1. So I can round off and make that m equals 1 and say that the reaction is first order in acetone. And the deviation away from getting exactly 1 is just experimental uncertainty. All right, so now you have all of the tools necessary to complete the advanced study assignment and have fun storming the castle.